Welcome to our video on the Fourier transform and frequency domain analysis, revealing the hidden frequency components of signals through mathematical transformation. Signals can be viewed in two ways: the time domain, showing amplitude over time, and the frequency domain, which reveals the strength of individual frequency components. The visualization on the right compares several common waveforms across both domains. The Fourier transform is useful for a periodic analysis, handling signals that don't repeat. It provides system insight, revealing energy at specific frequencies. Crucially, it's essential for filter design in both software and circuits to manage noise and extract features. The fundamental concept is duality and summation. Every complex physical signal is a superposition of simple sinusoids. The Fourier transform acts like a prism, decomposing a signal into its constituent colored frequencies. The forward Fourier transform converts a time domain signal, x of t, into its frequency domain representation, x omega. The integral formula achieves this by multiplying the signal by the analyzing kernel, which is a complex sinusoid, and integrating across all time. The inverse Fourier transform allows the original signal, x of t, to be reconstructed perfectly by summing all frequency components. This synthesis process uses a similar integral form, noting the positive exponent in the synthesis kernel. In short, the core signal philosophy is simple. The forward transform is analysis. It breaks things down. The inverse transform is synthesis. It builds things up. We move now to section 03, Conditions for Existence, which addresses the mathematical requirements for the Fourier transform to converge. The first Dirichlet condition is absolute integrability. The signal must have a finite total area under its absolute curve, ensuring the integral doesn't approach infinity. This means the signal must decay to zero as time approaches infinity. Dirichlet condition 2 requires finite discontinuities. In any finite interval, the signal must have a finite number of discontinuities. This prevents mathematical pathologies where signals jump infinitely many times. Dirichlet condition 3 demands finite maxima and minima. The signal must have a finite number of peaks and valleys within any finite time interval. In other words, it cannot oscillate infinitely fast between values. An important insight is that these conditions are sufficient, not strictly necessary. Many signals in engineering violate these rules, yet still possess a valid transform in the limit or generalized sense. Examples of special exceptions or generalized transforms include signals like the impulse or constant DC, which are not absolutely integrable. The impulse function transforms to 1 in the frequency domain, while the rectangular pulse in time corresponds to the sinc function in frequency. The linearity property states that the transform of a weighted sum of signals is the weighted sum of their individual transforms. This enables us to analyze complex waveforms by breaking them into simpler parts. Finally, the time-shifting property shows that delaying a signal in time results in a linear phase shift in the frequency domain. The magnitude or pitch remains unchanged, only its relative timing or phase is affected. The modulation property, the foundation of radio modulation, dictates that multiplying a time domain signal by a complex exponential shifts its spectrum and frequency. This allows signals to be easily translated up to high frequencies for antenna transmission. Conjugate symmetry is vital for real-valued signals. The negative frequency spectrum is the complex conjugate of the positive frequency spectrum. This implies the magnitude is even and the phase is odd. This conjugate symmetry leads to a crucial computation insight. Because real signals are symmetric, we only need to compute and store 50% of the spectrum, the positive frequency half. This significantly reduces computational load in algorithms like the FFT. The magnitude spectrum defines the strength of each frequency component. It is the absolute value of the complex transform result. It is often visualized as power spectral density. The phase spectrum defines the relative timing or alignment of each sinusoid component. It is calculated as the angle of the complex transform. Changes in phase can drastically alter the shape of the reconstructed signal in the time domain. A complete signal description requires both magnitude and phase to reconstruct the original signal perfectly. Think of magnitude as the colors of a painting and phase as the position of each brushstroke. Without phase, it's just a mess of color. Let's now work through a mathematical example, transforming a decaying exponential signal. We define our causal signal, x of t, as a decaying exponential multiplied by the unit step function u of t, ensuring the signal exists only for non-negative time. Step 1. Setup. We substitute the signal into the Fourier transform integral. Note that the limits change from -infinity to 0 to infinity due to the unit step function. Step 2. Integration. Combine the exponents and perform the standard exponential integration, leading to the expression shown. The final transform is found by evaluating the integral at its limits. Assuming a is greater than 0, the result is 1 divided by a plus j omega. The magnitude result is found by taking the absolute value of the final transform. This mathematically demonstrates a low-pass response, where the signal's amplitude drops as the frequency increases. The phase result is the angle of the final transform. This calculation shows the phase varies smoothly from 0 to -90 degrees, or -pi/2 radians, as frequency increases. The mathematical insight confirms that for a decaying exponential, the most significant energy is concentrated at low frequencies. The decay parameter A dictates the signal's bandwidth. In engineering, the Fourier transform is invaluable. It's crucial for communication systems, control systems analysis using Bode plots, and audio engineering tasks like equalization and noise reduction. Visually, the Fourier transform enables real-time spectral analysis of signals. It is also key in medical imaging and 2D filtering, allowing for image enhancement and feature extraction in frequency space. This concludes our deep dive into the Fourier transform and frequency domain analysis. We've reviewed the mathematical elegance and wide-reaching utility of this transformation. The key takeaway is that the Fourier transform is the bridge between the physical world of time and the analytic world of frequency. It successfully extends frequency analysis to non-repeating transients and real-world signals. We explored the core toolbox: linearity, where superposition holds; symmetry, where real signals have symmetric spectra; shifting, where timing changes phase; and the Dirichlet conditions, which define the limits of valid analysis. Thank you for engaging with this video on the Fourier transform, the mathematical tool of modern engineering. This slide provides the image sources used throughout the video, ensuring proper attribution for the visualizations and diagrams. We continue the image source list on this final slide.